Okay, so this will be the exam one review. So I'm going to go over the review that was posted on not Canvas or anything, but on the course website where your homeworks are posted. And I believe it's just called Review 1. So this has about 30 problems with a bunch of sub-problems. And so there's some I've chosen to skip over or only do a few of, but I'll talk about that when I get to it. So the first problem is mainly just asking about properties of the dot product. And I will mention that because there's so many problems, I think I'm just going to do the problems and write the solutions and maybe not spend so much time on the problems just to save time recording. And I'm using this stupid software anyway because my other thing broke, so I'm not sure if this will fully work out, but I think it'll be fine. So problem one just basically gives us a bunch of dot product expressions and then wants us to determine if they mean anything or if they're meaningless. And what that means is really just like, are they defined? So is the operation defined? Is it actually something that makes sense? Or is it something that doesn't make sense? So the first thing we have is just A dot B dot C. This doesn't really mean much. A dot B will be a scalar, and A dot B dot C will it's just attempting to take a dot product of a scalar with a vector, which is a meaningless operation. Dot product requires two vectors. Okay, next we have A dot B times C. This is meaningful, so this will be a scalar times a vector quantity. So A dot B will give us a scalar and C is a vector, and we can scale vectors. Okay, then C is the norm of A times B dot C. This is also meaningful. The norm of A and B dot C are both scalars, so their product is a scalar. Then we have A dot B plus C. And this is also meaningful, so we'd have B plus C is a vector, so A dotted with B plus C is a dot product of two vectors, which yields a scalar. And then we have A dot B plus C, so we just have some ambiguity with order of operations. And this would be meaningless because we'd have A dot B, which is a scalar, but C is a vector, so we'd be trying to add a scalar to a vector. So scalar plus vector, which is not defined. Okay, then finally we have the norm of A dotted with B plus C. This is also meaningless. The norm of A is a scalar. Dot product requires two vectors, so we'd have a scalar dotted with a vector, which is not defined for the dot product. Okay, and that's problem one. So now let's do part B of problem one, which is the same thing, but really about the cross product. So we'd have, let's look at the first expression, A dot B cross C. So this is meaningful. This will be what's called the scalar triple product. So this is the dot product of A and B cross C, and B cross C gives us a vector, so we'd be dotting two vectors, which is perfectly defined. And then we have A cross B dot C. This is meaningless. Cross product, like dot product, needs two vectors, but the dot product here yields a scalar, so we'd be trying to cross a vector with a scalar. Okay, then we have A cross B cross C. This is meaningful. This would just be a vector. B cross C yields a vector, so it would be crossing A with some vector, which is perfectly defined. Okay, now we have A dot B dot C. So this one's asking about dot product, but similar to what we were talking about with part A, this is meaningless. Dot product needs two vectors. B dot C is a scalar. Okay, now we have A dot B crossed with C dot D. Okay, so this is also meaningless. Both of these dot products gives us a scalar. We can't cross two scalars. Okay, and then we have A cross B dotted with C cross D. And this is perfectly defined. A cross B and C cross D will give us vectors, so we'd be dotting two vectors, which is perfectly fine. Okay, so problem 2 now is asking about some cross products, but we don't want to use the determinant definition that we've mainly talked about in recitation. So we want to use the fact that I crossed with J is K. J crossed with K is I. And K crossed with I is J. Your book talks about this property of the unit vectors. So the first problem that we want to find is I cross J cross K. So this would look, since we know that I cross J is K, we'd get K cross K, which by definition is 0. So that would be our answer. Next we'd have K crossed with I minus 2J, so scalar multiple of J. So let's just expand this a little bit. If K, or let's just say this is equal to K cross I minus, pull this 2 out, K cross J. So K cross I is J, so this would be J minus 2 times, and then K cross J would give us, so if J crossed with K gives us I, then K crossed with J gives us negative I, and this is something called the anti-commutative property of cross products. So if that's something you need a review up on, then I would take a look at that. So this will be minus I, which would come out to, you could write it as 2I plus J. Okay, there's our answer for that one. So next we have J minus K crossed with K minus I. Okay, so I think let's just use like FOIL on this. So this would be J crossed with K minus J crossed with I minus K crossed with K plus K crossed with I. Okay, so we get I and then minus, so that K cross K is going to go to 0, so we'd have minus negative K. Again, anti-commutative property, I'll just write the whole thing. So that term would go to 0, and then plus J, and then we could just add terms. So this would be I plus J plus K. Okay, so the last one is going to be I plus J crossed with I minus J. We'll do a similar thing. So this will be I crossed with I minus I crossed with J plus J crossed with I, and then that'd be J crossed with J, so minus J crossed with J. Okay, so we'd have 0 minus K plus negative K, again anti-commutative property, and then J cross J will give us 0. So this would just be negative 2K. And again, I know I kind of went over the solutions a little fast, but just for these ones, just use the definitions given. But then for these ones, we could just FOIL them out like in an algebra class. Just make sure you're preserving the operation. So usually when we FOIL, right, we're just doing regular multiplication, but in this case, we're doing this notion of vector multiplication through the cross product. Okay. Let's go to the next problem. So they give us a quadrilateral defined by the points A, B, C, D, and they give us that a vector A1 is AB, a vector A2 is the segment BC, A3 is CD, A4 is DA. And I'm just not going to be writing arrows for this video, just to save time. Hopefully it's clear from the context that we are talking about vectors. So this will be a vector formed by this line segment AB, etc., etc. Okay, so first they want us to graph A1 plus A2 plus A3. So this will be the tail to tip method. I'll give you what the setup is, and then try drawing this on your own, just using these straight line segments. So we'd have like the segment AB in BC gives us the segment A to C, and then AC plus CD gives us the segment AD. And so the sum of those vectors, A1 plus A2 plus A3 equals AD. So you should be drawing a vector from the point A to D. So try to see if you can do that on your own, just using this idea of the tail to tip method. Remember, right, we add a vector to its tail, and then the resultant vector is given by whatever this diagonal is. So I guess it would go in this direction if you were going that way. But this is what the result is for the sum of these vectors. Okay, then the problem also wants us to find what A1 plus A2 plus A3 plus A4 is. So we know that A1 plus A2 plus A3 is AD. So we'd have AD plus this segment DA. And this segment is essentially just you're going around a closed quadrilateral, which just returns to the starting point. So we say it's contained, so this would just be 0. Okay. Okay, now problem 4 is also more tail to tip stuff. So I'll just go over a couple of these, but you should try to do these on your own. So let's just do the simple one first. Let's just do A plus B. And I think they give us that A is like this vector. B is this like horizontal vector. And C sort of like points up and to the right at like a 45-degree angle. Okay, so A plus B will just be this vector A plus B, and so we get this new resultant vector here that would be A plus B. And then the only other one we'll do is, let's look at like A minus C. This would be A, which travels straight up, and then plus the negation of the vector C. So if C is pointing up and to the right, then its negation will point down to the left. So this will be, this vector A goes straight up, and then plus this vector C that goes like this. So this would be negative C. This would be A. And then this segment here is A minus C. And then there's some other problems on here, like B plus C, A plus C, and then like B plus A plus C, A minus B minus C. So try to do like B plus A plus C and A minus B minus C, especially using this idea. Remember that all we're doing is we don't really think of the multiplication as, or sorry, the addition as like actually adding components, but rather flipping directions for negative vectors here. So just try to do that with A minus B minus C, but this is more just practice. This is probably something you won't get on your exam. Okay, so problem 5 just asks us a bunch of stuff about vectors. So telling whether vectors are parallel, perpendicular, angles between vectors are acute or obtuse. So the thing to keep in mind here is that, oops. All right, this is 5. Given like vectors u and v, we say they're parallel if they can be expressed as equivalent to each other, and the only thing that's different between them is a scalar multiple. So we could say like lambda v. So lambda here would just be some real number, some scalar. So u and v are parallel if the only thing they differ by is their length, essentially. So they're parallel, they're going in the same direction maybe, but or they could be going in a different direction depending on the side of the scalar, but they can be different lengths as long as they don't intersect. And perpendicular, we know this from the dot product. So perpendicular, normal, orthogonal, all the same thing. Two vectors are perpendicular if their dot product is 0. If neither of those are the case, if their dot product is greater than 0, then the angle between them is acute. And if the dot product between them is less than 0, then we say the angle between them is obtuse. So let's look at like these examples they give us. So we get the vector u, 1, 2, 3, v equals 2, 4, 6. These are parallel, right? We could express v as simply twice of u, which would be the case. If we multiplied 2 into u, we'd get 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. So these vectors are parallel. What about the vector 1, 2, 3, and 2, negative 1, 0? Well, we can take their dot product. So this would end up being just 2 minus 2 plus 0. Their dot product 0, so it's orthogonal. And then the vector u is 1, 1, 0, and the vector v is 2, 1, 0. So their dot product is just 3. 1 times 2 plus 1 times 1. 3 greater than 0. And so we mentioned that if it's greater than 0, the angle is acute. And then finally, we have the vector 1, 0, 0. V is negative 1, positive 1, 0. So their dot product is just negative 1. Yep. So negative 1 is less than 0, and we determined that that means it's obtuse. Okay, so not much for this problem, just compute the dot product. And then for parallel vectors, you're not interested in computing the dot product. Just see if one vector is simply a constant multiple of another vector. Okay. Let's move on to problem 6. So they give us an equilateral triangle, so with vectors a, b, and c. And they also tell us the norm of A is 1. So in this equilateral triangle, all side lengths are equal, hence equilateral triangle. So this also means that the norm of B is the same as the norm of C, which is also just 1. So norm of B is equal to norm of C is equal to norm of A is equal to 1. And then the angle between A and C is 60 degrees, and this angle between A and B, and I'm looking at the diagram from the review sheet too. So the angle between A and B and it gives directions in the diagram, is 120 degrees. So we can just use the geometric definition of the dot product. So this would be the norm of A times the norm of C times cosine of 60 degrees. So we know these norms are 1, so we just have 1 times 1 times 1/2. So this would be 1/2. Would be the dot product. And the dot product between A and B, similarly, is norm of A, norm of B, cosine of 120 degrees. So this would be 1 times 1. And on the unit circle, 120 just rotates us to 1/2, but negative 1/2. So we just have negative 1/2. Okay. So then they also give us a square where A is the side length on the left going down, C is the side length on the top, and B is this half diagonal from the square center towards the bottom left. So, or from the top left, I mean. So the square side length is 1, and using Pythagoras' theorem, we can find that the diagonal is the square root of 2. So just think of that segment of that square as a triangle and use Pythagoras' theorem to get that. So this would mean that the length of B is 1/2 of root 2, or root 2 over 2. Okay, and this diagonal makes a 45 with each direction, 45 degree angle. So we want the norm of A cross B. This will give us the area of this parallelogram. So this will be norm of A, norm of B, and then for the cross product, we use the sine instead of cosine. And this will be 45 degrees, that angle formed by the diagonal. So this will be 1 times root 2 over 2 times root 2 over 2. And this comes out to 1/2. Yeah. Root 2 squared just gives, 1/2. Okay. And then we want the norm of C cross B. So this will be the same process. Norm of C, norm of B. Sine 45 degrees. 1 times root 2 over 2 times root 2 over 2. And this is also just 1/2. Okay. And so this problem asks us to determine whether it points into the page or out of the page. So this is sort of more of a notion that comes from like a physics class. If you're taking like physics 2 about E and M, you'll talk about this, but you can use the right hand rule. So take your right hand out and have your thumb pointing up and match it to the orientation of the diagram. So A cross B would give us negative 1/2. So into the page. And C cross B would be negative 1/2 into the page, I believe. There's probably like a video on YouTube of someone doing it. I can't really show a video of my hand, but it's not too important for this class, but that's the exercise I wanted to do. So you just take your hand, and when you curl, imagine curling your hand and use your thumb sort of as like the axis of rotation, or in this case, your thumb would be the z-axis pointing up. And when it says into the page, that just means that if you imagine there's like an imaginary sheet in front of you, when you curl your hand in the direction of the magnitude in this case, are you curling into that page or are you curling away from it towards yourself? Kind of weird to explain, but okay. So problem 7, more dot and cross product stuff, just using angle stuff. So they tell us the norm of A is 5, the norm of B is 10, and then they give us theta is 26 degrees. So A dot B is just 5 times 10, so 50 cosine 26. And the norm of A cross B is same thing, 50, but now sine of 26 degrees. Okay. And so from the diagram, at least, rotating from A to B is clockwise. So A cross B would point into the page. Be negative K. Okay. And then part B gives us norm of A is 6. Norm of B is 8. And that theta is 150 degrees. Okay, so A dot B is 6 times 8, 48 cosine of 150. And norm of A cross B will be the same thing, 48 sine of 50 degrees, sine of 150 degrees. Okay, so in this case, A cross B points also into the page. So in the negative kth direction, maybe, if that helps. Okay, now problem 9 is asking about two methods that can be used to test if a triangle given by the segment ABC is right angled. So we can think of this in terms of dot product and then Pythagoras' theorem with like regular triangles in geometry. So we can compute side vectors and then test if they're perpendicular or not at some point. So if like, we'll say this is problem 9. If the segment AB dot AC is 0, meaning that segment's orthogonal, then it means there's a right angle at A. So, right angle. Right angle at A. Similarly, if we had like BA dotted with BC being 0, then we would have a right angle at B. And then you can probably see the pattern. So if we did it for CA and CB, if their dot product was 0, then their right angle would be at C. So we're always focusing on this in our order of operations. Okay. And then the next thing we could do is just, if we know the length of those segments, i.e. the norm of the segment A, B, B, C, CA, etc., then we can just use Pythagoras' theorem. So A squared plus B squared equals C squared, where A, B, and C would be like the norm of AB, the norm of BC, and like the norm of CA. So if we had those side lengths, we could just substitute them into this and use Pythagoras' theorem. Okay. So problem 10. So we're given that, I'll just read the statement. C lies on a segment AB and is twice as far from B as from A. In other words, the segment BC is twice the length of AC. So we can let little a be from the origin to the point A, little b be from the origin to the point B, and little c be from the origin to the point C. So because C is on the segment AB, then AC is the same as AB, and they just differ by some multiple, some constant multiple, which I'll just call T in this case. And this would be for some T that's greater than 0, but we'd want it to be less than 1. Okay, so we can now find an expression for CB. So CB would just be the same as AB, but by some algebra, we'd have that it's a constant multiple of 1 minus TAB. Just use the definition from above. And so now we want the norms. So length of CB would be, we can ignore the scalar, 2 times the length of AC. So this gives us that CB is 1 minus T, so we'd have 1 minus T equals 2 times, and then we found that the norm of AC would be just T from the definition above. Okay, so this gives us an actual expression for T. We do some algebra. So this would be that T is 1/3, I think. Okay, so AB, displacement B minus A. AC, again, displacement little c minus A. So little c minus A would be 1/3 B minus A. So C is A plus 1/3 B minus 1/3 A, which would be 2A plus B over 3, which is the expression that this problem is asking us to essentially show that those segments can be expressed by this vector, given by this vector equation 2A plus B over 3. Now, this is sort of just from fundamentals derivation, but you can also use something called like a segment formula or a mid-segment formula. I think it talks about it in your book. There's a bunch of stuff online about it. But I wanted to give a more general derivation just so you sort of know how to do it. Okay, problem 11 is kind of a joke. It tells us, it gives us a diagram. From the diagram, going along U, then V, it says to express W in terms of U and V. This is just like our cookie cutter vector addition. So W is the resultant vector of U plus V. That's the whole answer to this problem. There's really nothing to it. W is that vector that's formed on the diagonal by summing those two vectors. Okay. So problem 12 gives us a diagram, and it wants us to find a resultant force. So let's look at the diagram. So we have that the norm of this force F1, which is a vector, but it's just going to be capital in this case, is 3 at an angle of 120 degrees, and that the norm of F2 is 4 at an angle of 45 degrees, as seen from the diagram. Okay, so our first vector is F1, which is 3 cosine 120 degrees sine 120 degrees. Just remember the x and y components of your vector. So this would just be -3/2, 3√3 over 2. And then this vector F2 is 4 times cosine of 45 degrees and sine of 45 degrees. So this would be, what is that, like, yeah, 2√2, 2√2. Okay. So the resultant force, sometimes given by this notation, is just the sum of all the forces. So just F1 plus F2. Okay, so this would just be the vector 4√2 minus 3 over 2, and 4√2, what would this be? 3 plus 3√3 over 2. Okay, and then they want us to find the magnitude. So, okay, the magnitude is just the norm of the resultant. So that would be square roots of... Okay, now there's some annoying arithmetic going on in the background here, but this would be 25 plus 6 times square root of 6 minus root 2. And if it's not clear where those came from, try looking at this first. You don't have to, you can just plug straight in, but try looking at this expression first. So squaring the norm, and then that'll let you simplify these a little bit better. Because these square roots, if we square it, it'll be nice, because then we have like root 2 squared is just 2, or root 3 squared is just 3. And then we can plug that back into this actual expression for our magnitude. Okay, that's all. No, then it also wants this angle. So it wants the elevation angle, so that's the angle from the x-axis. So this has a nice formula. That's just tangent of theta is the y component divided by the x component. So that'd be 4 root 2 plus 3 root 3, 4 root 2 minus 3. So theta would be the arctangent of all of this, which is, if you have a calculator, you can go ahead and plug that in. But I don't have a calculator, so I have no idea what that is. Okay. So nothing crazy here. Just remember that we can express x and y components as some multiple of cosine theta or sine theta for the y direction. Okay. So problem 13 is asking about areas and volumes with orthogonal vectors and parallelograms. So it wants us to find the area of this parallelogram first, with vertices A being the points -3, 0, B, C, D. Okay, so what can we do? So we can take the adjacent sides from A, firstly. So we could say A to B is the vector 2, 3. A to D is the vector 6, -1. Okay, so the area of this parallelogram is famously given by the magnitude of the 2D cross product. So this would be, say our area is 2 times -1 minus 3 times 6, the absolute value, which would be +20. Okay. So now we're given, for this next question, it's still part of 13, but a point 3, 1, 1, Q 5, 2, 4, and R 8, 5, 3. So we want an orthogonal vector to the plane through those points, and then we also want the area of the triangle PQR that's formed by the composition of those points. Okay, so we first want, similar to part A, we want PQ. So this would be the displacement. So this would be 2, 1, 3. And then we also want PR, which would be the vector 5, 4, 2. So a normal vector is given by the cross product, right? The cross product always yields some vector C that's perpendicular to the input vectors, say A and B. So in this case, we're thinking of these actual segments here as our vectors. So we're looking at PQ cross with PR, which comes out to be -10, 11, and 3. So So one non-zero orthogonal vector would be this vector here, given by negative 10, 11, and 3. Okay, so now the triangle is, if we know the area of the parallelogram is the norm of the cross product, then the triangle area is just 1/2 of that. Same way as just in regular geometry, right? The area of the triangle is just half base times height. We think of this now as, so I'll say area of this triangle is 1/2 PQ cross with PR. So we know what that vector is, PQ cross PR, so we just want it to norm. So this would be 1/2 times negative 10 squared plus 11 squared plus 3 squared. So this comes out to be 109. Okay, so this would be like 230, square root of 230, and then times 1/2. So I'll just divide the whole thing by 2, and that's our answer. Okay. So next we want the volume of the parallelepiped from the vector A is 1, 2, 3. B is negative 1, 1, 2. And C is 2, 1, 4. So the volume of this parallelepiped is actually given by the triple product, which is something that we saw like in problem 1 or 2, I think. So the volume is given by, and specifically we're always, when we're thinking of these area or volume notions of parallelograms and parallelepipeds via like the dot product and cross product, we're always looking at their magnitude, because volume and area is a scalar. It will not be a vector. It will always just be some number. So the volume is given by the norm of A dotted with B cross C. This is what that triple product is. And, you know, for good exercise, find what B cross C is on your own, and then dot it with A. That should just be a scalar product, but you should find that this is equal to 9. So all you need to find is what B cross C is, and then what A dot, whatever that is equal to. We'll give you some scalar, in this case 9. And that's our volume. Okay. So problem 14 is sort of just a conceptual problem. So it's just asking for the geometric meaning of dot and cross product and these quotients. So if theta is the angle between these two vectors, A and B, and their dot product is given by norm of A, norm of B, cosine, that looks really weird, norm of B, cosine theta, and norm of A cross B is A, B, sine theta. So we're looking at A dot B magnitude divided by norm of A. We can write this as B cos theta. So I guess the geometric, I'll just say this in words. The interpretation would be that this is the magnitude of the component, or the scalar projection of B along A. Okay. And then we have, I want us to look at A dot B divided by the norm of B this time instead of A. So this would be norm of A cosine theta. And so this would be just the opposite of what I just said. This would be the magnitude of the component of A along B rather than B along A. Okay, then we have norm of A cross B divided by norm of A equals norm of B sine theta. And if you're wondering, I'm getting these expressions, just use these facts up here and substitute. Okay, so this would be the, how would I say this? The magnitude given by the norm of B, the component of B that is perpendicular to A. Remember that this notion of the cross product, we should always be thinking of perpendicular vectors. So this would be the magnitude of the component of B that is perpendicular to the vector A. And similarly, we have, what is going on? Okay, great. This is awesome. My pencil disconnected, which means I can't write anything. Okay. So, okay, I'm back. So this is the second part of the video, I guess, technically. So that was all of problem 15, though. So we can move on to 16. But this, I don't know, I'm using this stupid software that I've never used. But problem 16 just wants us to show in 2 dimensions that the square of the norm of A cross B is just the norm of A squared times the norm of B squared minus A dot B all squared. And so it says in the xy plane, so that means that we can consider these vectors in R3, but we'll just we'll zero out the zth component. So we can let A be A1, A2, 0, and we could let B be B1, B2, 0. And so basically this is just going to boil down to substitution and some algebra. So I think I'm just going to go through it and yeah, okay, so. Okay, so basically we found all the individual parts. So I needed the square of the norm, I needed the square of the norm of the cross product, I needed the dot product, and I needed the square of the norm of B as well. And then I just substituted that in terms of A1, A2, B1, B2, etc. for this expression. And we can just distribute everything, and we end up with the expression A1, B2 minus A2, B1 all squared, which is definitionally the square of the norm of the cross product. So this would complete our proof. Okay. So that's it really for this section on just basic vector stuff. This first part of the review is more just sort of simple vector stuff, but now we'll actually use vectors talking about lines and stuff, lines and planes. So problem 17, we want a line in R3 through a point x naught, y naught, z naught. with a direction vector A, B, and C. So this is prime time to use our function r of t being r naught plus tv, which in this case would be our r naught would be our point, x naught, y naught, z naught, plus t times our vector given by a, b, c. Okay. And this problem isn't even really asking for any specific example, but just to sort of break down the process of doing this. So we can use this equation. We also can extract the parametric equations from this, just based off the components of these vectors. So this would be x equals x naught plus at. So x naught would be this component here, the first component of our point. A is the first component of our vector, and then t is still the scalar multiple. And we'll do the same down to z equals z naught plus like ct. Okay. And the other thing that I'd mention is that as long as a and b and c are non-zero, then there's a symmetric form of these parametric equations given by the following. So that'd be x minus x naught over a equals y minus y naught over b equals z minus z naught over c. And so, this is situational like everything, but this can be nice for some equivalent relations. Okay. So let's look at an actual example. So problem 18 is asking about a plane that goes through a point with a normal vector, a normal being that it will be perpendicular to that plane. So we say that a point xyz lies in the plane if and only if that normal vector a, b, and c is in fact normal. It's orthogonal to the vector given by the displacements between those points. So in this case, it'd be like the vector x minus x naught, y minus y naught, z minus z naught. So, and the orthogonality condition comes from the dot product being 0. So we're going to carry that notion here. So this would be, I guess I'll write everything out so it's more clear. So we have the point x, y, z, and a vector that we're assuming to be normal, ABC. So we say that point is in the plane if the following is true. A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Equivalently, we could distribute this and make it a little simpler. So this would be ax plus by plus cz equals some value d, where in this case d would be given by these initial points. So a x naught, b y naught, and c z naught. So these are all equivalent in that case. Okay. So let's move on to problem 19. So this is about line segments. So problem 19 is exercises 17 and 18 from 12.5. So the first exercise is asking us to find a vector equation for the segment from the point 6, -1, 9 to the point 7, 6, 0. So, and it goes in the direction AB given by the vector 1, 7, -9. Okay, so this line would be given by the equation r of t being 6, -1, 9 plus the scalar t times 1, 7, negative 9. And we're usually assuming that t is either greater than or equal to 0 and less than or equal to 1. Okay. So now we want the second question, 18, wants the parametric equations for a segment given from the point given by -2, 18, and 31 to the point 11, -4, 48. So this will be the same process as what we just did, but we're just going to jump straight to the parametric part. So remember, the parametric equations are just extracting the components. And the problem also gives us that it's in the direction of a vector AB being 13, minus 22, and 17. So this would look like our first parametric equation would be x equals -2 plus 13t. Y would be 18 minus 22t. And z would be 31 plus 17t. Okay, so fairly straightforward as long as you know what I was talking about here for the parametric equations and the vector equation. Then it's just a matter, at least in this problem, of just substituting those values. Okay, let's do problem 20. So this is exercises 69 and 70 in the book. So they want us to use the formula from earlier, which it says in the book is from 12.4.45, but that formula is this distance formula given by the norm of the segment formed by P naught P. So this is, keep in mind, this is a vector crossed with direction vector V and divided by the norm of that vector V, where V is the line's direction vector and P naught is the point on that line. Okay, so we're given for 69 a point P being 4, 1, -2, and our line would be x equals, I'm going to use the parametric equations. That's what the book's using, 1 plus t, y equals 3 minus 2t, and z equals 4 minus 3t. And we take p naught to be 1, 3, 4. That's the initial point. And this vector v to be 1, -2, -3. Okay, so after we have the whole setup, we just need to know what P naught P is and what P naught P crossed with V is and the norm of V. So P naught P, the segment, is 3, -2, -6. Displacement. Okay, and then we can cross this with V. So P naught P crossed with V would be -6, 3, -4. This is a simple enough example to where you could probably just use the algebraic definition, but you can use the determinant definition, which I'll go over in some examples later. But the main calculation we want is this distance d. So the norm of that segment crossed with V would be given by square root of 61. So we're looking at taking that vector -634 and just taking the square root of the sum of the square of all the components. So 36 plus 9 plus 16. So square root of 61 over, and now the norm of V. V is that vector 1, -2, -3, so it'd be 1 squared plus 4 plus 9, so we'd get square root of 14. And I'll just leave it like this. I think you could simplify that. You could probably rewrite it as something over 14. I don't know what that something would be though. Actually, let's just do it. Oh, I see. Yeah. So this would be the square root of 854. Either one is fine. Okay. So now 70, so this is part 2 of that problem. We're given a point now, P being 0, 1, 3. Line x equals 2t, y equals 6 minus 2t, and z is 3 plus t. We take p naught to be the point 0, 6, 3, and this direction vector to be 2, negative 2, 1. Okay, we're doing the same process again. So we need p naught p. In this case, it's 0, negative 5, 0. We need p naught p crossed with v. Again, use whatever method you think is easiest. Negative 5, 0, 10. Here I'm just using the component definition, the algebraic one, not the determinant. And then we're going to use that distance formula again, and we'd end up with 5 root 5 all over 3. Yeah, because that'd be 9. So 3. Okay. Nothing crazy, really just plugging into this formula. Okay, let's talk about problem 21 now. So this is exercises 71 through 72 in the Stewart book in 12.5, talking about distances from a point to a plane. So we can describe this plane. So for plane AX plus BY plus CD, plus CZ equals D, and a point X naught, Y naught, Z naught. Their distance can be expressed as just the magnitude of these scalar multiples of all the initial points. So AX naught plus BY naught plus Z naught. And then that initial equation, we're just moving the D over from the right side, so it would become minus that point D. And then we divide this by essentially the norm of all those initial points. So this would be the square root of a squared plus b squared plus c squared. That's capital C squared. Okay, so 71 gives us some values to use. So we're given a point 1, negative 2, 4, and a plane given by 3x plus 2y plus 6z equals 5. So we'll just plug into our formula. So this would be 3 times 1 is 2 times negative 2 plus 6 times 4 minus 5 all over square root of 3 squared plus 2 squared plus 6 squared. So what would this be? This would be 18, and this would be 49, 7. So 18 over 7. And I'll leave 72 to you. This would just be redundant. So this is the point negative 6, 3, 5, and they give us a plane x minus 2y minus 4z equals 8. So try to find out what this distance is between the point to the plane using this formula. So just do what we just did. Just plug this in. See if you get it should be, you should try to get something like 40 over square root of 21 or some other simplification of that. Okay. So let's look at problem 2. So again, distance between planes and a point, but now we're talking about parallel planes specifically. So again, if this is a plane, we'll distinguish this by saying this is D1, and this is a plane. They're parallel. If they are parallel, then their distance is given by the norm of D2 minus D1 over the square root of a squared plus b squared plus c squared. Okay, so they give us 2x for 73. They give us 2x minus 3y plus z equals 4. And then they give us 4x minus 6y plus 2z equals 3. So we have two planes, so how do we do this? All we really want to do is divide the second plane by 2. So we want to consider 2x minus 3y plus z being 3/2. Okay, and this makes sense. If we divide that equation 4x minus 6y plus 2z, we just get back the first plane. But now this 3 is a 3/2. And so this sort of matches up with our notion of things being parallel, where they're essentially equivalent, but they just differ by some scalar multiple. So what would the distance be in this case? We'd have 4 minus 3/2. So our first distance, which is 4, and our second one is 3/2. And then 2 squared plus negative 3 squared plus 1 squared. So this comes out to 4 minus 3/2 would be 5/2 divided by square root of 14. And I'm sure there's a nicer way to rewrite this. Actually, let's just do that now. In proper fraction, so I'll write it as this. But I think either is fine. Okay. Now try and do the same on your own for 74, but this time we're given the plane 6z equals 4y minus 2x and 9z equals 1 minus 3x plus 6y. So the hint I will give you is that you should rewrite this. So try to rewrite it to look more like this form up here. These forms. And then do the same process. Just look at, okay, what do I need to divide by in order to make this plane be equivalent to the other one? And then plug it into the distance formula. And you should get something like root 14 over 42. Or some equivalent to that. Okay. So problem 23 is asking all about lines. So this sort of actually jumps back in the book as far as the examples we were just doing. So this is examples 19 through 22. I'm only going to do 19 and 22 just for the sake of time. But this is just trying to determine if these lines are parallel, skew, or intersecting. So I'll do 19 and 22, and then maybe you can go and see if you can do the others on your own. But we're given a line L1 is x equals 3 plus 2t, y equals 4 minus t, z equals 1 plus 3t, and then another line L2, which is x equals 1 plus 4s, y equals 3 minus 2s, and z is 4 plus 5s. Okay, so the direction, we're given direction vectors just from these parametric equations. So v1 being 2, -1, 3, and v2 being 4, -2, 5. So these direction vectors are not scalar multiples of one another, so they're not parallel. We know that. And we can actually solve this by setting everything equal to 0 to see where they intersect. So take these, and this is a good algebra test. Take all of these lines and solve individually by setting everything equal to 0. Solve this system. And we find L1 and L2 are skew. Okay, now 22, we're given a line x over 1 equals y minus 1 over -1 equals z minus 2 over 3, and that L2 is x minus 2 over 2 equals y minus 3 over 2 equals z over 7. Okay, so we have this sort of like symmetric thing going on. So again, we can look at just how to express these lines individually. So let's look at like L1. This would be 0, 1, 2 plus t times 1, -1, 3. L2 would be the point 2, 3, 0 plus the scalar multiple that's been called s times a vector 2, -2, 7. Okay, so the direction vectors are not scalar multiples as well, and same process as 19, the intersection equations actually lead to a contradiction if you set everything equal to 0 and solve. So we'd also say that these lines are skew. So L1 and L2 are skew in this case. And I think in 20 and 21, there's an example of parallel lines. And so that should be that they are a scalar multiple. Or if they're intersecting, they'll share a point in the plane. Okay. So problem 24 is also asking about intersection points. So this is 24. So we're given a line given by the vector equation r is 1, 1, 0 plus t times 1, -1, 2. We're given another line. So this would be r is 2, 0, 2 plus s is -1, 1, 0. Okay, so we can match components very easily in this vector. So that would give us that t is equal to 1 and s would be equal to 0. So their intersection point would simply be 2, 0, 2. Given by this vector here. Okay, now we also want to find a vector perpendicular to the plane. So again, we should be thinking of cross product. So this vector n, and usually we denote this actually as n hat, like this, indicating it's a normal vector. So this would be vector 1, -1, 2 crossed with the vector -1, 1, 0 from above. And we should find that this is -2, -2, 0. So we could use n equals 1, 1, 0. It'd be in a point normal form is what your book calls it, with the point given up here, 2, 0, 2. So what this would look like is we'd have dot product between 1, 1, 0. And this is equivalent. We're just dividing these terms by -2 in this case. So you'd have 1, 1, 0 dotted with, now we need the displacement, so x minus 2, y, and then z minus 2. Okay, so this dot product evaluates to 0, which implies, at least if we do the algebra, that x plus y is equal to 2. So this would be our equation. And so we found an intersection point between these two lines, and then we found an equation for the plane that contains those two lines. And so the process for finding that plane is we need a vector that's normal to the plane. So in this case we found one by the cross product. And then we need the dot product, which yields a scalar. So if we have scalar values in there like x and y, it will actually give us an equation for a plane, which in this case is just a simple plane x plus y is 2. Okay. So more plane stuff for 25. So we're interested in an intersection line and then also the angle between two planes. So we should know that the angle between two planes equals an angle between normals. Essentially, this normal vector is a perpendicular vector, but when we're looking at their magnitude of their dot product, we can get actual algebraic expressions for a plane. So we'd say cosine theta is equal to n1 dotted with n2. And then we divide by the norm of those normal vectors, n1 and n2. Okay, so we're looking at examples 57 through 58 from 12.5 for this problem 25. So 57 gives us the following. Okay, so we can subtract these two equations. So this will give us y plus z equals 0. So z is -y. And we can plug this into the first plane. So we can have x plus y minus y equals 1. So x equals 1. And if we let y equals t, then z, which is -y, would just be -t. Okay, so we have now this vector equation. So this essentially holds true as long as our initial point is 1, 0, 0. Right? All of these have 0 scalars here, other than the actual t value here, except for this first one. X is just exclusively equal to 1. So we'd have 1, 0, 0 plus t times 0. And then we're just looking at the sign of these. So we'd have 1 and -1. Okay. So these are sort of two things we can consider. Okay, and then now we need the normal vectors. So our n1 would be, we could use the vector 1, 1, 1. And our n2
would be 1, 2, 2. Yeah. Okay, so now we can actually use this equation. So we're really just trying to find the angle between these two planes. So cosine theta will be the norm of the dot product between those unit vectors. So n1 dot n2 will give us positive 5. So we'll drop the absolute value bars. And then we're looking at the norm of n1 times the norm of n2. The norm of n1 will be 3. So we'll have 3 root 3 we can write. And because n2 would be 1 squared plus 4 plus 4, 9, which would be 3. So we'd have 3 times square root of 3. Okay. And then theta, of course, is just the arc cosine of this. Whatever that equals when you plug it into your calculator. I think the problem might say to put it in degrees to like 1 decimal place. That's obviously just sort of specific to the problem, but okay. So 58. We then have, and this is still part of problem 27. So we have 3x minus 2y plus z equals 1, and then we have 2x plus y minus 3z equals 3. So let's let z be t, similar to how we did in the last problem. And so we'll solve the following. We'll solve 3x minus 2y equals 1 minus t. I just moved that z over to the right side and let it equal t. And then 2x plus y equals 3 plus 3t. Okay, so this gives us x is 1 plus 5/7 times t. Y equals 1 plus 11 over 7 times t. And then we have z just being t. Okay, so now we'll rescale the direction vectors. So this will be r equals 1, 1, 0 plus, I'm going to use lambda this time. Lambda is just some scalar. This will be 5, 11, 7. So I'll write here to the side that lambda is just some scalar. Okay, and then we'll have normal vectors. 3, negative 2, 1. Normal vectors. And 2 being 2, 1, negative 3. And we need their dot product. This nicely just evaluates to 1. And the norm of this first unit vector would be 9 plus 4, 14, so square root of 14, and same with n2, so these norms are actually equivalent to each other. It's just the square root of 14. So this means that cosine theta is, again, we're using the norm of the dot product, so this would just be absolute value of 1 over square root of 14. And of course theta would be, again, the inverse or the arc cosine of whatever this is, 1 over 14. Okay. So 28, we're sort of getting introduced to vector functions now. So this is wrapping up the review, but we're basically asked to find the domain of some vector valued functions and then some limits. So this is exercises 1 through 4 in 13.1, and then exercises 7 through 12 in 13.1. I'm going to do exercises 1 through 4, and then for 7 through 12, I'm just going to do problem 7 and 12. Okay, so for 1, this would be, we're given the vector function ln, holy shit, ln of t plus 1 and t over square root of 9 minus t squared, and then 2 to the t. So we have a natural logarithm, some rational expression, or not rational, but square root, and then an exponential expression, 2 to the power of t. Okay, so we just want the domain. So the domain, a vector function is like satisfied as long as the domain of all the components exists. So for the natural logarithm, remember that the natural logarithm is undefined at 0. So it has a root at 1, ln 1 is 0, and it's undefined at 0. So for this t plus 1, we just want this to be greater than 0, which implies that t is greater than negative 1. Okay, for this next expression, we just want the denominator to never be 0. We don't want to divide by 0. So we want 9 minus t squared to be greater than 0. So this means that move the t squared, take square root on both sides, so we'd have negative 3 is less than t is less than 3. So t needs to be greater than negative 3 and less than positive 3. Okay. And so the intersection would give us, in this case, t needs to be greater than 1. So we can put this all together as saying that t must be greater than negative 1, which is greater than negative 3, so it's fine. And then also it needs to be less than 3. And so this is a perfectly valid answer. Okay, so now we're going to look at the domain of this vector function being cosine of t times I plus the ln of t times j plus 1 over t minus 2k. So again, this is just the same thing. They're just using this ijk notation. Okay, so t needs to be greater than 0, that natural logarithm, and t cannot equal 2. Cosine of t can take on all real numbers, so we'd have, this is 0 to 2, and then we'd cut it with a union, and then this would go 2 to infinity for that cosine. If you're unfamiliar with this notation or just forgot it, please ask me. But this is just a way to express like interval notation. Okay. So now problems 3 and 4 are asking about limits of vector equations. So they asked us to calculate the limit as t approaches 0 of the vector given by e to the minus 3t I plus t squared over sine squared of t j plus cosine of 2t k. Okay, so this is finally the first actual calculus we think we've done in this class so far. And this is super simple. For limits of vectors, we're just looking at the limits of the individual components. So if one of the limits of one of the components doesn't exist, and we say the limit of the entire equation doesn't exist. So component-wise, we'd have, I'm just going to drop the t approaches 0. Just note that this is all t approaches 0. We'd have the limit of e to the minus 3t. Direct substitution would give us e to the 0, which is just 1. Okay. And then we have the limit of t squared over sine squared t. So if we sub in sine of 0, this would give us 0 undefined. You can use L'Hopital's rule on this if you'd like, but we can also express this as the limit of t over sine of t squared, and this comes out to 1. And then we'd have the limit of cosine of 2t. This is perfectly defined. Cosine of 0 is just 1. So then our limit is the vector given by 1, 1, 1, because all these limits evaluated to 1 in this case. Okay. Next, 4 is also a limit, so we have the limit as t approaches 1 of t squared minus t over t minus 1 I t plus 8 j plus sine pi t over the natural logarithm of t. Okay, again, we'll go component-wise. So this first limit, we would have a indeterminate form. We could do some algebra on this. Or you could use L'Hopital's if you'd like. But one thing that we can know is that t squared minus t over t minus 1 equals t, so t can't be 1. And we find that its limit does evaluate to 1. So use either some algebra on this or L'Hopital's if it's simpler. Then we have the limit of the next component, which is root t plus 8. This is perfectly fine. We could do direct substitution. This would be the square root of 9, which is just 3. And then we have the limit of sine of pi t over ln of t. And so for this, I would use L'Hopital's rule. So this would come out to pi cosine of pi t by the chain rule. And then remember that the derivative of ln of t is 1 over t. And so now we could do a direct substitution. This would just be pi of 1 times negative 1. So just negative pi. Okay, so then the limit of this vector is itself the vector 1, 3, negative pi. Okay, now for these last two parts, this has examples 7 through 12, but we want to, I'm just going to do 7 and 12. This is more of like a drawing / conceptual thing, so, but I'll go over these first two. So like we're given r of t is negative cosine t. So this is a sideways cosine wave minus cosine t. It's bounded by between negative 1 and 1. But then the equation y equals t increases linearly. So we can think of this sort of in R2 as looking something like this. Sort of like a spring. And so the vector would be going this direction. Okay. And then the next one that I'll go over is, they give us the equation r of t is sine of pi t and cosine of pi t. So now we should immediately think, okay, we're in R3. So note that the equation of a circle, like x squared plus z squared equals 1. So the curve would be like a helix whose radius is 1, and this would wrap around the y-axis. And again, similar to the first time, we have this t component, so this would be y equals t, meaning it would rise linearly.
So it's sort of going to be inspired like from the previous example we just drew, but in R3. So maybe we can imagine this as sort of in a cube. So let's imagine that's really bad. Let's do like this. Okay. And then this would be like the imaginary line sort of drawing this together. Very bad, but you can imagine this is sort of like a room with walls. I'm just really bad at drawing. But in R3, what this is looking like is, I guess we should say this is probably X, this is Y, and this is Z. We're going to have this spiral again, sort of that we got from this first one. But rather than it looking like a spring, it is going to actually look like a spiral. So it'll be probably something like this, on and on and on. And so it's growing linearly via that y equals t. It makes this helix, and it's bounded between, it's bounded by sine and cosine of pi t. So the other examples that are similar to this just do the same process, but I recommend using things like Desmos as a really good online tool. Okay. And let's do problem 30 now. So 30 is simple. It just asks us to define what curvature is. So for a smooth curve that is parameterized by an arc length, which if you haven't talked about arc length yet, you will, but the curvature is usually defined by this Greek letter kappa, which when I draw just looks like a normal K, and this is just the magnitude of dt ds. Okay, so and t is what's called the unit tangent vector. But in general, for just some general parameter like lowercase t, like a scalar, and as long as the line describing that its derivative is not equal to 0, then we can say that the curvature, still defined by kappa, is the norm of the derivative of my line crossed with the second derivative, both evaluated at t, divided by the first derivative again of r, and this time we cube this. And so the geometric meaning would be like the curvature measures how quickly the direction of motion changes. So it's a radius of curvature, which sort of makes sense in an intuitive way. If we think about like a sheet curving over if you dropped like a blanket over an exercise ball and its curvature, the blanket draping over the ball, we can measure that with this derivative, usually with t being the tangent vector. Okay, so that is review 1. Again, I know I didn't do all the problems. That's because a lot of the review problems, it just asks you to do a bunch of exercises from the book, which a lot of them are just reviews of the exercises that are directly listed in the review. But of course, we'll talk about this in recitation too. So just email me if you have any questions.